Thank you very much. I appreciate the invite from Nature and from NASA. I think my talk's going to be a little different than all of the talks we've heard so far, so maybe now's a good time to get a cup of coffee if you start to get tired. So I'm an applied biostatistician. I used to work here at NASA for several years, and now I'm at the University of Michigan, but really a lot of my work in Michigan is very similar to the way I used to work here at NASA, in that I'm a collaborative team scientist. I team up with various researchers who are trying to test their hypotheses with the data at hand. So you guys are all microbiologists, and a lot of the things I'm seeing here are way above my pay grade, but hopefully some of the things I'll say will be good takeaways for you. Have you heard the news? There's a big debate going on right now in the scientific literature about p-values, and it's not a new debate by any stretch, but it's really coming to the foreground in some big science publications like Nature. This is a 2014 paper that sort of got a lot of people's attention about how maybe we're making a lot more mistakes than we think we are, or at least being a little over-reliant on p-values and the normal way that we go about science. That was in 2014, and then later in 2015, there was a journal in psychology that actually banned the use of p-values. Have you guys heard about this? Yeah, it's really. Yeah, right. And then when this came out too, I was like, wow, man, that's a little bit like throwing the baby out with the bathwater, right? But they're very serious about this. And at the time, if you wanted to publish in, I think it was Behavior and Applied Social Psych, they would accept your manuscript if it had p-values and significance in it. But if it was going to get accepted for publication, those things would be removed. So they were very serious about this. And this was back in 2015, but it was a response from decades and decades and decades of misunderstanding, misreporting p-values and an over-reliance on them. So a little bit later, the American Statistics Association, my primary professional association, in 2016 released a statement on p-values. And this was really an unusual event for the ASA. We don't do this kind of thing. We don't make public statements. I think there was one other public statement that I'm aware of from the ASA, and that was following the presidential election in 2009. So that was the only time they ever sort of came up and said, hey, you guys need to be paying attention to statistics. Otherwise, we're a pretty quiet group. And I'll talk a little bit more about this today, but that was in 2016. It was a big deal for the ASA. We had over 150,000 times this p-value statement was viewed online. It's been cited a whole lot of times. So, the ASA went, wow, we're getting a little bit of attention from this, I think if you Google this, on Google Scholar, you'll see it's about 2,000 times it's been cited in various manuscripts. But, that was in 2016. And then later in 2016, another Nature publication came out. I'm going to talk a little bit about this, where 1,500 scientists were surveyed about the reproducibility and reliability issues. And what do we think about this? I've got a few statistics about this too. So this stuff is really coming to a head. It's really bubbling up. And then later, or earlier in this year, in March of 2019, the ASA released another statement. Wow, in my lifetime, hey, this is pretty cool. So I'm going to talk about this a little bit. But, something's happening in science in general. At least 50% of the scientists, those 1,500 scientists that were surveyed, believe that we're in a crisis of reproducibility. A crisis of reproducibility. Think about that. These are scientists. This is not just like various specific news agencies that you might hear on television talking about science. One of our primary tools for scientific inquiry, the null hypothesis statistical testing, is currently under siege. And in fact, we love acronyms at NASA, right? NHST, that's, reject the null hypothesis. Some have argued that we should use a different acronym, and it goes statistical hypothesis inference testing. And it's under siege. There's a lot of people that are finding issue with this. Of course, you guys are talking about a lot of big data analytics, right? And that brings up a whole lot more p-values. And so if we're not using p-values correctly, it may deliver a lot more problems than perhaps we're giving attention to. And then, of course, here we are at NASA, right, with tiny n. So that, of course, affects p-values. What are we going to do now? Are we done? Do we just pack up and go home, or what should we do here? So what's the trouble with p-values, right? I mean, we're all smart people. PhDs go through a lot of training, even if they're not getting trained in statistics per se. Virtually every PhD program that I'm aware of has at least some statistical training at a fairly high level. But still, we really misunderstand what p-values are and what they mean. And because of that, we We often misuse them. Sometimes, most of the time, I think unintentionally, we do p-hack. You know what p-hacking is, right? We look and we see a batch of p-values that bubbled up to be significant, and then who here's not curious, right? We all got to try to figure out why that happened. And so we try to hypothesize after the results are already known. They call that harking. And you know, we do all this because I think in part a lack of an understanding of p-values and what they mean. We oversimplify decisions. We go to defaults. We really are kind of lazy cognitive misers in a way. We just kind of go with, well, this is the way we've always done it, so let's just keep doing it this way. We really do fail to appreciate, I think, a lot of the contextual factors that go into p-values and what generated them. So I'll talk a little bit about that. But it's not just the scientists. It's journal editors. It's funding agencies. We perpetuate this problem. When we teach statistics, we perpetuate this problem. For one, we discourage publishing non-significant results. And so we have these garbage can studies that never get published, but might be really informative. And not only that, not just that, but all of the tests that we run before we publish, and we only publish the 2 or 3 or 4 things that were significant. This doesn't happen in your lab, I know, but it probably happens in other people's labs, right? Whew, not us. We deflect from the p-value problem often by offering really oversimplified solutions. So I'll talk about some of those solutions and why they don't necessarily work. But here's a big one. We're still teaching this stuff. We're still teaching this in statistics. I still teach statistics, and I'm telling you, this is part of every textbook that I pick up. And so it's hard to kind of avoid that problem. And then, of course, big data. All those promising results that are out there, it's so rich. There's just so many things we can learn from that. But yet, we don't have time to do it all in a super, super thoughtful way. So we rely on p-values to tell us what's important to pay attention to. And we have these problems with p-values. But not us, right? I mean, the people in this room, we are the smartest scientists that are out there, so we don't make these mistakes, right? Well, please indulge. Don't answer out loud. You may embarrass yourself. But let's just go really, really simple. You've got 2 treatments, treatment A, treatment B. You're trying to compare them on some important outcome variable. You get a p-value on that comparison of 0.032, so true or false. The most appropriate statistical procedure here is a 2-sided test, right? We all learned that. That's the most appropriate test, right? Well, actually, false, usually. We typically force 2-sided tests, but that's a dogma sort of thing. We tend to do that to make it really hard, have a smaller region of rejection on either side of the tail. But you know what I say? If you want a small region of rejection, then make a small region of rejection. It doesn't have to be done sort of default by a 2-sided test. That's sort of it kind of leads to our misunderstanding of what p-values are. How about this one? The chance of a false positive incorrectly rejecting the null is about 3.2%. Well, you're probably too smart for that one, right? No, that's false, but it's interesting why it's false, right? A p-value is a measure of compatibility between the null hypothesis, the thing that you're trying to reject, and the particular data set that you're working with, reflecting at least that large of a difference. And so the chance of a false positive could be approximated by a power analysis with all that goes into a power analysis, proposed effect size, variance estimates, and stuff like that. But it's not something that you get by the p-value. And yet people make mistakes like this all the time in their conclusions and when they're writing things up. This one's easy. We should report this value, as this result as p less than 0.05, right? I mean, there's the p-values right there, 0.032. Shouldn't we report that as p less than 0.05? No, why should we do that? When somebody says, how much do you weigh? Do you say, I weigh less than 300 pounds? Or do you tell them how much you weigh? I mean, it depends how much you weigh, I suppose, right? But, scholars in this field have come around to say, the p less than 0.05 is disguising information. Why don't just give the information? What is the p-value? Just tell us, please. Don't make us guess how much you weigh, right?
Can you elaborate on that a little bit? How much data do you get out of reporting the p-value?
I would report the p-value at least to levels of precision that I think are reasonable. So if that does depend on sample size and your measurement metrics and things like that. But I would say p equals, and then what does it equal? In this case, I would say point.
No, but why? Why? If you read a paper and you had these specific p-values, it's interesting.
I personally think it's hiding information. That's my personal bias on this. You're throwing away information. You're dichotomizing. When I know I don't have a whole lot of time, so remind me though. I'll tell you about my weight loss example. That's the one I always give when I teach this stuff. The probability that treatment A is equal to treatment B is 3.2%, right? Because we got a p-value of 0.03.2, that makes sense, right? But actually, no, that's not true at all. P-values are not the probability of the null being true. The null might be true, the null might not be true, but p-values are just a measure of compatibility between what the data would look like under that null hypothesis and the data is at least as extreme as what we're getting. So these are all, you might think they're subtle, but they're all mistakes. There's a few more, please bear with me. How about this one? There's a 3.2% probability that chance alone produced the differences that we observe. Now that comes really close to the way a lot of people talk about results, right? But actually, that's also false. It's actually a backwards argument. P-values are generated assuming that only chance differences exist, and we're typically hoping to reject that with our data. And so to claim that there's a systematic, and to claim that there's a difference, but a p-value is not the probability that chance differences exist. That's actually part of the null hypothesis testing procedure to begin with, right? So it's kind of reverse logic, but it leads to our misunderstanding of things. How about this? A significant test result suggests that the null hypothesis is false and should be rejected. Actually, it doesn't. A p-value is simply a measure of compatibility between what we expect under the null, given that all of the assumptions that are in play are true and met, and the data at least extreme is what we've observed. So there's lots of reasons why we can get a small p-value and still be in that null hypothesis scenario. And this is why if you've worked with statisticians on papers, they always, if they're sort of card-carrying statisticians, they always go through a very careful assumption testing. Now, the only assumptions we can test are the quantitative assumptions associated with the test, but there's a lot of assumptions that go into play in the null hypothesis testing procedure, like for instance, random assignment to groups. Well, any of those assumptions in the whole experimental context that aren't met might result in a small p-value that has nothing to do with the null hypothesis. All right, how about let's turn it around. Let's pretend that the p-value wasn't 0.032, but it was something big like 0.72. Now, that would be evidence in support of the null hypothesis, right? That the two groups are not different. Not true. Large p-values simply suggest that the data are not unusual under the null hypothesis, but they might also be not unusual under many other null hypotheses, not just the one that you set up to test. That one kind of tricks people a lot when you don't think about this for a living, right? We detected a statistically or substantively important difference. I think most scientists know that that's false, right? We don't equate significance from in a statistical way as meaningful in a clinical way or a scientific way. Oh, just a couple more. The interpretation of p-value is true regardless of how we allocated subjects to treatment groups. I mean, we get the p-value, we get the p-value, we get the p-value. If I give the data to you and you and I both do the same test, we're all going to get the same p-value. So it doesn't really matter how we allocated subjects to groups, right? But this is false because the whole p-value, the whole null hypothesis statistical testing procedure assumes all of the pieces and parts of an experimental design, and random allocation to groups is one of them, right? If we were to evaluate a different outcome in this same exact study, and on that test it had an even smaller p-value, then that indicates that that outcome changed more, right? Wrong, because p-values are also a factor of variance and effect sizes. So we can't use a p-value in place of an effect size measurement. It just doesn't work that way. Are these a little bit tougher? If you had several studies conducted in different labs testing the same exact hypothesis, and very few or none of them achieved a significant result at the P05 level, then that suggests evidence in support of the null hypothesis that there is no effect. Now, that seems legit, right? Your lab and her lab and his lab all are doing the same hypothesis testing, and very few of them, maybe none of them have P05. That suggests no effect, right? And if you've done meta-analysis, you know right away, yeah, that's not true. It could be that there's a very small effect. Perhaps the measurement, the outcome measurement that you're using has a low signal-to-noise ratio, so you're not going to get a tiny p-value in all of those studies, but yet there could be a very systematic effect that's being repeated over and over and over again. It's just too small to reach that critical P05 level, right? What if you had two studies conducted with two different subject populations? One had a significant result at 0.05 and the other didn't. This would be called conflicting results, right? Oftentimes, researchers do this, right? They see research, a paper over here that found an effect and a paper over here that didn't find that effect, so this seems to be conflicting, right? Well, actually, this is usually false. It could be true if all of the assumptions in both models were the same, but there could also be very subtle things that are different between these two studies. A small difference in standard error, for instance, could cause the p-value to, in one case, be less than 0.05, and the other case to be greater than 0.05. Now, if I had started giving you the actual p-values, this would become more obvious to you. One of them had a p-value of 0.051, and the other had a p-value of 0.049. One study is worthless, and the other study is fantastic, right? It's because we had that cutoff, right? And so there's a lot of common misconceptions about p-values. They're not as reliable as we think they are. We assume that p less than 0.05 supports the alternative hypothesis when it doesn't. We assume that p greater than 0.05 supports the null hypothesis when it doesn't. We assume less than 0.05 equates to an important effect when it could just be statistically significant, but really unimportant in any practical way. We assume that using alpha 0.05 is always the right alpha, and we also assume that we always need to be doing a two-tailed test significance, that's the right strategy all the time, everywhere. We are confused about what chance probability really means and how it relates to p-values. We have a lot of confusion about bigger and smaller p-values being evidence of bigger and smaller effects when they're really not. We get messed up about how they relate to effect size and meaningfulness. I think sometimes we equate p-values with the probability of a false positive, and they're different ideas. And we really fail to appreciate that every p-value that gets generated is inherently connected to all of the assumptions about the statistics employed and the test and also the experimental design. We miss that one a lot, unfortunately. And so some have argued for a simple solution: get away from p-values and start reporting confidence intervals. Are we any better at understanding what a confidence interval is? I teach statistics. I'll tell you, it's not an easy subject to get across, but we're all smart, so we know how to do this, right? Well, how about this? Let's say that you abandon p-values, and now you're just going to build yourself a habit of always reporting the 95% CI, and that's going to be the solution here. So a 95% CI, we have to know what that is, right? So a 95% CI calculated in my study has a 95% chance of containing the true effect, right? That's what it is, right? No, not really. The true effect is either inside your confidence interval or it isn't. So the true probability is either 100% or 0%, right? You've created a 95% confidence interval on your sample, and if this study was to be replicated over and over and over and over and over again, everybody calculating the 95% CI, then if you look at 95% of them will contain the true parameter that you're trying to get. But in your one study, it's either there or it's not. How about this one? An effect outside the 95% confidence interval is refuted by the data. In other words, a bigger effect or a smaller effect is rejected. Nope, that's false too, because a 95% confidence interval from any single study does not suggest that the true effect is inside it. It's related to the one we just talked about. What if you have two overlapping confidence intervals? If they're overlapping with one another, then that suggests that the differences are not significant, right? I get this one a lot, right? They shouldn't overlap unless they're the same, right? But actually, that's not at all true. It's highly possible to have overlapping confidence intervals between two groups that would be statistically different at the 0.05 level. Now, if either the lower or the upper bound of one group overlapped the point estimate, then you would have a non-significant result. What about this one? Two non-overlapping CIs mean that the difference from the group would be statistically significant. Is that true? Yeah, it is. Did I shake your confidence a little bit? That suggests maybe we don't understand CIs as well as we should. I had to put one true one in there, right? How about this one? An observed 95% CI predicts that 95% of the estimates from all future studies will fall within that observed interval. No, it doesn't, right? A 95% CI from any one study makes no prediction about the point estimate of some future study. It was never intended to. What about the last one here? A 95% CI that includes the null value, for instance, 0, no difference. That one must be more precise than a 95% CI that doesn't include the null value. Nope, sorry. A 95% CI is precision. It's how precise can we estimate the interval. And we're as precise at estimating a non-difference as we are estimating a difference, right? So if we're going to use confidence intervals, we have to get less confused about them, right? And so it's not a simple solution, right? I think in part, one of the reasons that leads to our confusion about confidence intervals is that we've always picked 95%. And we've mentally connected that with the 5% alpha. And so a lot of the errors that we make about alpha mentally are just connected and brought over into the errors we make about confidence intervals too. But they're really different constructs altogether. Now, I will say that part of the solution to the p-value problem does involve confidence intervals, I think. That's one good possible way we should be moving. But we have to understand them better, and we have to interpret them better so that we don't kind of make the same mistakes with confidence intervals that we've been making with p-values, right? So it's not just a surrogate. We have to understand it better. So let's go back to March of 2016 when the ASA released this first opinion piece. This is a quote from that. It said, "The p-value was never intended to be a substitute for scientific reasoning." The ASA executive director said, "Well-reasoned statistical arguments contain much more than the value of a single number and whether that number exceeds some arbitrary threshold." And so in 2016, the ASA statement was designed to shake up the science world a little bit and say, hey, stop just looking at the 0.05 and use your brain the way you want to use it. Don't use p-values of 0.05 or not 0.05 as sort of like your gatekeeper to sharing knowledge, right? And so we released these 6 principles that we wanted people to pay attention to. Principle 1, p-values can indicate how incompatible the data are with a specified statistical model. P-values do not measure the probability that the studied hypothesis, the alternative hypothesis, is true, or that the probability that the data were produced by random chance alone. They never did that, they still don't. We want scientists to remember that scientific conclusions and business or policy decisions should not be based only on whether a p-value passes some threshold, and that proper inferences require full reporting and transparency, so the exact p-values, and not just the ones that are significant, those other ones that you ran too. P-values or statistical significance do not measure the size of the effect or the importance of a result, and by itself they don't provide a good measure of evidence regarding a model or a hypothesis. So this was in 2016, and I'll ask you, these 6 principles, there was lots of additional text, by the way, that gave some suggestions on how to improve things, basically emphasizing that we should be focusing on effects magnitude and precisions of measurement and things like that. And we were encouraging people to consider some alternative methods as well, Bayesian being one of them, but just one of them. Decision theory was another one. And instead of focusing on alpha risk reduction like Bonferroni corrections, false discovery rates. So this was all in 2016. I'll tell you, it was widely viewed. We had a ton of citations. There was a lot of attention from ASA. But what's happened in your lab? When you submit grant proposals, do they still want you to do that power analysis? The fun part of the grant, right? When you submit papers to be reviewed for publication, are you submitting the ones that don't have p less than 0.05? Or are you just focusing mainly on the p of 0.05? What about when you're the reviewer? I mean, you know this, right? I'm not telling you guys anything new. Are you reviewing papers differently now? I can tell you, from my experience, everybody's still carrying the P05 card. They're still carrying it. There was a time in my training when I considered getting a custom license plate that said 95 CI or P05, right? It's really pervasive. We can't seem to shake the P05 thing, right? So guess what? ASA got pissed. And in 19, they've expanded their recommendations. Read this. They say that the 2016 statement on p-values stopped just short of recommending that declarations of statistical significance be abandoned. We take that step here. We conclude, based on our review of the articles in this special issue and the broader literature, it is time to stop using the term statistically significant. Nor should any variance, like statistically different, p less than 0.05, non-significant, survive. No asterisks in tables, even. I saw some asterisks on graphs here today. Okay, this is the time to look at your watch, take a deep breath, This is not just some obscure psych journal. This is the American Statistics Association recommending no more statistically significance, wording, asterisks, or references in tables, right? Now, in case you're wondering, the ASA is a big, big group. We've merged with the Royal Statistical Association, so we're the biggest professional association in the world, right? We're the second oldest. Mass Medical apparently beats us there. We have 18,000 plus members in government, academia, and the private sector. We have prestigious journals. We have prestigious meetings. Past presidents, these are people that you know, even if you're not a statistician, like Wilcox, Wilkes, Cochran, Likert, Box, Kruskal, all the big names, right? So our leaders are pretty highly qualified, pretty smart people. Our journals and meetings are widely read, heavily attended. If you've got statistical colleagues, they know about this, right? Our members, we sit on review teams and we advise scientific panels. And we've been around long enough to recognize that this need is here. So it's time to get on the train, right? We need to be thinking about a world beyond PO5, right? So what should you do about it? Well, I'm providing some citations for you here. I really think you should start reading. And start with the 2019 paper, special issue in the American Statistician, right? This is not written for statisticians. This is written for scientists. So it's very approachable, right? We've got a statement by Ronald Weiserstein of the ASA Executive Director, and it's followed up by very short, but many articles, 43 articles written specifically on this issue, plus 22 additional articles and books. Very, very approachable, okay? I highly recommend it. Here are the three overarching principles, though. I'll summarize. Accept uncertainty, be thoughtful, be open. What do we mean by accepting uncertainty? There's no easy button in statistics. Erase from your brain the idea of a statistical certainty, because actually that's the opposite of what the statistics are doing. The statistics are not going to remove variance from your data. They're going to help you understand the variance in your data, right? Get rid of the binary idea that there either is an effect or there isn't effect. It's a curve, right? There's a probability associated with it. And seek better ways to quantify, visualize, and interpret the effects that you're seeing. Don't just report, for instance, the 95% CI, but focus your interpretation on it. What would it mean if the effect was as small as the lower part of your 95% CI? Practically, what would it mean? What would it mean if the effect were as large as the upper boundary on your 95% CI? That's the kind of talking that gets you thinking and your readership thinking as well. In this dedicated manual, there's lots, like I said, 43 plus 22, a whole bunch of different things. So I tried to pick out things that sort of resonated with me. Anderson, in this article, tells us we should be asking 3 questions of our research and the stuff that we're reading from others. What are the practical implications of the estimate? And I'm reminded of a quote that I really never knew the author from, but in order for there to be a difference, it has to make a difference. So think about that. Is the difference that you've identified in the confidence interval boundaries around it, is it meaningful? Is it impactful? Because if it's not, we probably shouldn't be paying attention to it. But if it is, I don't care what the p-value is, tell me about that, right? How precise is our estimate? This is a quote from Rob. Precision is your new power. When you're asked to do that power analysis for your next grant proposal, turn it on its head and do a precision analysis. Precision is basically saying, with the sample size that I project I'm going to be able to use for the money that you're giving me, this is how precise I'll be able to estimate the effect. Whatever the effect is, it might be huge, it might be small, this is my precision. It's actually easier to calculate than power because it requires one less thing. The one thing that the statistician always asks you about, and you go, Rob, if I knew what the effect size was, I wouldn't need to do the damn study, right? Well, you don't need effect size to do a precision analysis, so I want you to think about that. Also, is the model specified correctly? Because this is where p-values get calculated and they're completely incorrect if the model's not specified properly. There are other really thoughtful approaches, though. I say think like a beer brewer, Gossett. Do you know who Gossett is, by the way? He used to work for Guinness. Student, exactly. He published Student's Tea. He wasn't allowed to publish under his true name at Guinness. So he had to come up with another name, and he considered himself a student of statistics, so he published under the name Student. And, you know, he wasn't a big p-value fan either. In fact, he had 10 principles that he thought every research study should strive towards. And Zeliak brings us back to those 10 principles and says, let's kind of come up with a way to rate ourselves as a high G value instead of a small p value. Maybe a little less, I think, practical, but I think it's useful to look over what some of those practices are. Consider alternatives to p-values that still provide a quantitative assessment of how valuable your data are, but not with p-values because we're so dang confused about p-values, right? So some argue for multiple null hypotheses, not just that the null hypothesis of no difference, but multiple null hypotheses that all of them would be worthy of discarding for some alternative hypothesis. I really like this idea. Consider rescaling the p-value to a completely different scale, but still using the information that the p-value derives for us so that we understand the value of our data. And one of them that I liked was called the S value, and this is like the Shannon information criterion. Literally, it's the negative log base 2 of your p-value. And I'll tell you how to interpret it. So let's say you had that p of 0.034 from my earlier example. If you take log base 2 of that and negative, you get an S value of negative 4.87. And what that tells you is that the result that we get from our data, if the null is true, is about as surprising as flipping a coin 5 times and getting 5 heads in a row. So it's really very much an understandable metric. If you got a smaller p-value, it'd be maybe 10 times as unlikely. Am I running out of time? Okay. There are lots of other recommendations about thoughtfulness, but I'm just going to sort of brush over them. Multi-stage analyses, p-values plus effect size, meeting both of those criteria and stuff like that. Replacing the idea of confidence intervals with compatibility or competence or compatibility intervals helps us better read our results of confidence intervals and understand them properly. And then being open in terms of transparency. The ASA is recommending that journals, particularly for online publications, have a replication function where when you publish your study, you also publish the data, and then others have the opportunity to reanalyze your data and replicate or not replicate your result. And guess what? Either way, it's useful information. And you get credit for data that's been replicated or not replicated because it's true value in science. I'm going to jump ahead to NASA and our small n problem. To me, this is all good news because we've been hypersensitized to small n and the problem with p-values. We already know this. And so now the rest of science is coming around to us, right? We struggle to find publication outlets and we understand the problem with small n. However, I'm going to move to some of the good things. We're a small group. And so I think because we know that p-value is a problem, we can change things quickly. We're not the NIH, right? The NIH it's going to be a hard thing for them to change everything. But NASA does direct funding to research calls, and we can quickly impact how that works. We can start to respond quickly to implement changes in terms of what we require of our grant proposals and how we review those grant proposals with regard to power analysis and p-values and things like that. Nature Microgravity can think very fast about implementing the changes recommended by the ASA in terms of how we review stuff and to try to get some of the openness and replication stuff going. We can move much quicker than sort of the bigger science places do. And the idea here is that we're trying to get to the world beyond this dichotomy that a study with 0.05 0.051 is a worthless study, and a study with a p-value of 0.049 is really wonderful science, right? We're trying to get beyond that so that regardless of what your p-value was, you can share meaningful results with the community. And I think this is possible today when it's easy to publish online, it's easy to share lots of information. So yeah, I'm running out of time, but that's really my concluding remarks on the p-value dilemma and how it relates to small n and NASA.